So first, I'm going to remind you what a polynomial is. A polynomial is a function that uses only addition, subtraction, and multiplication. A polynomial is a function that uses only addition, subtraction, and multiplication. So if there's a cosine in the function, it's not a polynomial. If there's division in the function, then it's not a polynomial. So it's got to have just addition, subtraction, and multiplication. And it could be repeated multiplication, so there could be a power, like x to the third is just x times x times x. So it's okay to have powers because that's just repeated multiplication. All right, so those are polynomials. And the reason I bring those up is all polynomials are continuous. And they're continuous everywhere. So they're continuous on the interval negative infinity to infinity. So all I'm saying there is that if you have a function that uses addition and subtraction and multiplication, when you draw the graph, it's going to be totally connected. There's not going to be any jumps or asymptotes, infinite discontinuities, or what was the third? Oh, there won't be any removable discontinuities. Okay. So that's true for all polynomials. So if someone says, is this function continuous? If you recognize that it's a polynomial, it's going to be a really quick answer. You're just going to say, yes, it is continuous because it's a polynomial. Now, other functions are trickier, so you have to do what we did yesterday with those. But with polynomials, it's a piece of cake. Okay, so then the main topic for today is a theorem called the intermediate value theorem. Intermediate value theorem. So when you hear the word intermediate, what does that mean to you? Somewhere in the middle, right? Okay, so this is called intermediate because it has something to do with the middle. And when you have a value, that's referring to the y value. So the intermediate value theorem is a theorem that's about the middle y value. Okay, so whenever you have a theorem, there's an if part and a then part. And if you meet the requirements here, then you get this for free. So with the sandwich theorem, there were two requirements. And then if you met both of those requirements, then you get the last part for free. So the same thing's going to happen with the intermediate value theorem. There's going to be a couple of requirements here. And then if those requirements are met, this comes out for free. All right, so the first requirement is that f of x has to be a continuous function. And it may not be continuous everywhere, but at least it has to be continuous for an interval. So we're going to say it's continuous from A to B. And this just means that maybe A is 0 and B is 7. So that means in between the x values 0 and 7, the graph is connected. Maybe it's not connected out on the edges, but at least in between 0 and 7, it's connected. Okay, so you have a function that's continuous on an interval. This isn't a point, it's an interval, so it's two x values. Okay, so you have a function that's continuous on an interval. That's the first requirement. And then the next requirement talks about a y value. And that's a y with a little 0 below it. And that's called y sub 0. It's short for y subscript 0. But I'll say it quickly. I'll say y sub 0. And then sometimes it's called y naught. That's more so in physics class. The 0 is like a naught, like a nothing. So occasionally you might hear me, but probably more often a physics teacher, call this y naught. And you might say, why do they call it that? And I would say, why not? So that was the first bad joke of the year for you. Oh no, there's been others, sorry. So anyway, we're focused on this y value. And what we're trying to do is we're trying to hit this y value. So maybe this is 7. So we are trying to see if 7 gets hit. And since it's called the intermediate value theorem, that means this y value is in the middle. Okay, so we want this y value to be in the middle between two other y values. And the other y values that it's the middle of is the y value at A. So remember, A is an x value. So if I plug A into F, that gives me a y value, right? The y value at A. So there's the y value at A, and here's the y value at B. And this number needs to be in the middle between those. That's why this is called the intermediate value theorem, because the y we care about is in between two other y values. So we're going to say that that y value is smaller than that, and that y value is smaller than that. So again, this mathematical sentence right here is where the theorem gets its name. It's the y value in the middle, the intermediate y value. Okay, so let me draw a picture of this situation. So we've got a function that's continuous in between a and b. So maybe a is about 2, maybe b is about 10, and we know we have a connected function between those values. And then we have our y value at a, so that's called f of a. And then we have our y value at b, and that's called f of b. And then we just have some other y value that's in between those. So I don't know what it is, but let's say it's this one. So we just have a middle y value between those two y values. Okay, so those are our requirements. We have to have a y value in the middle, and we have to have a continuous function. I haven't drawn the function yet because I want to make my point in a minute, but it's connected between there and there, according to this requirement. Okay, so here's what happens for free. What has to happen is that y value has to get hit. So if I'm going to draw a continuous function from here to here, it would be impossible for me to do that without hitting this height. I could avoid it for a while, right? I could stay down here for a while. But eventually, I'm going to have to cross that height. Well, unless I jumped over it. But why am I not allowed to jump over it? Because I have a continuous function, right? So what you get for free is the fact that this y value has to get hit. So the fancy way to say that is then there is a c, that's an x value, where f of c, so that's the y value at c, equals this y value. Okay, so now I'm going to finish drawing my picture. I don't know if the picture would have to look like this, but let's say it connected like that. So now, where is C in this picture? Let's see. So here's my height, right? And then here's my x value, that outputs that height. So on this picture, this is C. C is the x value that outputs the height we're trying to hit. So is everybody okay? Do you see where that is now? So I could draw a different picture and there'd be a different C value. But all I'm saying with this theorem is that there has to be a C somewhere that'll reach that height. Because that's the only way I can draw a connected graph from this dot to that dot. Okay, so this is about the y value in the middle between two other y values. All right, so that's a famous theorem called the intermediate value theorem. So now we're going to do a problem that involves the intermediate value theorem. But at first, it's not going to look like it's using that. So the question is any real number exactly 2 less than its fifth power? Is any real number exactly 2 less than its fifth power? Is any real number exactly 2 less than its fifth power? So that's the question on the tape. Okay, so we need to try to answer this question. And like I said, it's connected to the intermediate value theorem, but at first it looks not like it's not connected. Okay, so I'm going to call the real number that I'm looking for x. And the question's asking about the number, x, and its fifth power. So that's x to the fifth. So we have our number x, and we have the fifth power of our number. We're not sure what the number is yet, so that's why I'm calling it x. So here it is, and there it's fifth power. Okay, now you have to read pretty carefully. This is a tricky question. Which one of these is needing to be bigger? See, is any real number 2 less than its fifth power, right? So they're asking they need this one to be less, 2 less. Is everybody okay? All right, so the one on the right, sorry, the left, my right, your left, the one on the left is smaller. How much smaller? 2 smaller, right? Okay, so how could I even them out? How could I make this side equal this side? Add 2 to the smaller one, right? Okay, so if I add 2 to x, then apparently it needs to equal x to the fifth. X was smaller than its fifth power, and it was 2 smaller, so when I added 2 to it, it evened it out. Okay, so I'm trying to find a number that'll make this true, so that if I take the number plus 2, it'll equal the number to the fifth power. Okay, so now I'm going to rearrange this, and I'm going to subtract the x to the fifth over to here. And I'm going to have the negative 2 end up over here. So this is just another way to word the question. Could I have a number minus its fifth power equal negative 2? All right, now I'm going to make up that and call f of x this function. I'm just pulling this out of thin air. I'm calling f of x x minus x to the fifth. So I'm just calling this function over here f of x. Okay, is this function continuous? How do you know? You're right. How do we know it's continuous? Because it's a polynomial, right? It only's got multiplication, x times x times x times x times x, and subtraction. So this f of x is continuous because it's a polynomial. So you can see I'm sort of getting towards the intermediate value theorem. Because for the intermediate value theorem to work, I need to have a continuous function. So that's happening. I've got my first requirement here. And it's not only continuous in between for a small interval, it's continuous everywhere. So that's a bonus. Okay, now what y value am I trying to hit? What am I trying to output here? -2, right? I need this mess to equal -2. So the y value I'm trying to hit is -2. So my y0 is -2. That's the y value that I would like this function to hit. Because if this function can output a -2, then I'll have that this is true, which will mean that this is true, which will mean that this is true. Because all of these say the same thing. This is the words, this is the algebra, and then that's the rearranged algebra. But they all say the same thing. Okay, so I'm trying to hit -2. So if I'm trying to hit -2, I need an x value that spits out something less than that, right? And then I need a different x value that spits out something bigger than that, so that this one's in the middle, so that this one is intermediate. So I'm just going to try some numbers, and I'm kind of blindly trying numbers here. And it's just an experimentation. Okay, so let me plug 0 into my function, because that seems like that would be easy, right? So if I plug 0 into my function, that's going to give me 0, because 0 minus 0 is 0. Okay, so is that the larger one or the smaller one? It's larger than -2, right? So I found a number that would spit out something bigger than -2. Now I have to find something else that'll spit out something smaller than -2. So I might not find it right away. So let me try f of 1 and see what happens. So if I plug 1 in, that's 1 minus 1, which is 0. So that was unproductive, because I found another one that was bigger, right? Okay, so that wasn't good. Let's see, how about if I try 2? So that's going to be 2 minus 32, right? So -30. So that's good, because that's smaller than -2, right? Okay, so just to frame it in the theorem sense, I've got my y0, and it's less than f of 0. I've got my -2, which is less than this, right? And it's bigger than f of 2. So my a and my b are 0 and 2, right? Okay, so here's the situation. I have 0 spitting out 0, and I have 2 spitting out -30. 0 outputs 0, and 2 outputs -30. And I want my function to hit -2, right? Is this function going to hit -2? How do you know? Because it's a connected graph, right? And there's no way to get from that point to that point unless you could delay the inevitable for a while. You could procrastinate for a while, right? You guys are good at that. But then eventually you're going to have to hit -2. I don't know if it looks like that, but eventually you're going to have to hit -2. So we got both of these requirements, right? The function's continuous, and we got this requirement. So we get this for free. So now we know there is a c somewhere between 0 and 2 So by the intermediate value theorem, and the IVT is completely fine for abbreviating the intermediate value theorem. Even on the AP test, they understand IVT means intermediate value theorem. Okay, so by the intermediate value theorem, there is a C on the interval 0, 2. So somewhere in between 0 and 2, when you plug C into the function, that's going to hit negative 2. And so that means that if I plug that number into here, it's going to equal negative 2, which means that if I plug that number here and here, those would be equal to each other. So that means that that number is the number that's exactly 2 less than its fifth power. So the answer is yes, there is a number that will do that. Now this is very unsatisfying to people, because when I first gave you this question, you were thinking you were going to find the number, right? The question is there a real number exactly 2 less than its fifth power? And certainly if you could say, yes, here it is, it's 1.798, then that would answer the question, yes. But I didn't do it that way. I just demonstrated that it existed without actually finding it. But that's okay, because the question said, does it exist? It didn't say find it. Now again, if you had found it, it would prove that it exists. But we proved that it exists without finding it. That's okay, because it just said, does it exist? Okay, so the final answer is there is a number that is exactly 2 less than its fifth power. I didn't find it yet, but I know it exists. Sorry, that's the possessive it. It doesn't have a apostrophe. Okay, then there's a part 2 to the homework question that's like this, and it says find the number to 3 decimal places. All you have to do is graph this function in your y equals, and then graph negative 2 in your y equals, and then calculate the intersection point, right? You with me? So just put this in y1, put that in y2, and then calculate the intersection point. Then you don't actually find the number then. You only get the number to 7 decimal places. The number's irrational, so it goes on forever. But they asked you to find it to 3 decimal places or something on the homework. So make a quick note, because you know how it's frustrating when you get to the homework and there's something that's not exactly like what we've done in class. I'm sorry about that. It's a necessary evil. Maybe by the end of the year you'll sort of buy in, but right now you're kind of annoyed by that. I get it. So anyway, I'm trying to help you out there. Y equals y2, calculate intersect. Okay, but the real big deal here is that this theorem, this intermediate value theorem, is an existence theorem. What I mean by that is it proves that something exists. And there's another big deal existence theorem in calculus that we'll find later. But for now, this is our existence theorem. It's called the intermediate value theorem. It comes up a lot. Okay. Just a few more facts about continuous functions. So if f and g are continuous functions, if f and g are continuous functions, then, so maybe f is 3x plus 2. So it's continuous. And then maybe g is a different function. Maybe it's x squared. The way you can do is you can create a new function by adding those together. And that function is called f plus g. So in my example, that would be 3x plus 2 plus x squared, I think, if I remembered what I said before. So you got your f function and your g function, and you add them together, and that creates a new function called f plus g. And if f is continuous and g is continuous, it turns out that f plus g is also continuous. So then f plus g is also continuous. Also, if you subtract the two functions, you could create a new function. So let's say this one's 3x plus 2, and this one's x squared. The new function would be 3x plus 2 minus x squared. That's called f minus g. And if f is continuous and g is continuous, then the new function f minus g is also continuous. And also, if you multiply the two functions together, you get a new function that's continuous. What do you think comes next? Division, right? So you have this function 3x plus 2 and this function x squared. If you create a new function 3x plus 2 divided by x squared, that new function is continuous, unless what happens? Unless g is 0, right? So this is also continuous unless g of x is 0 at some number, like then it would mess things up. Not allowed to divide by 0. Division by 0 messes us up everywhere. Okay, that's enough for today. We get to leave at 8, so you still got a couple minutes to ask questions.